Hello and welcome to this Optica Technical Group webinar, Unconventional Photonic Information Processing using Silicon Photonics. My name is Makai Pruitt and I'm excited to welcome you to today's webinar, which is hosted by our Nonlinear Optics Technical Group. The technical group has invited Peter Bienstman from Ghent University to speak with us, and we'll begin our presentation in just a moment. As you may know, Optica's technical groups have been hosting weekly webinars for many years now. Our group volunteer leaders organize and host these webinars to help bring you the latest in-depth information related to your specific research interest. In addition to these webinars, we host a wide range of virtual and in-person activities to help you connect with your fellow Optica members. We hope that you'll visit us at optica.org/technical groups to learn more about the 40+ groups, find out about our upcoming events, and access our library of over 200 on-demand webinars. Now, before we begin today's presentation, I wanted to review a few housekeeping notes. First, we will be addressing all of your questions for our presenter after their talk. We encourage you to submit your questions for our presenter throughout the webinar, and you can do so by clicking the Q&A button at the bottom of your Zoom window. You will then be able to submit your questions in the pop-up box. You will also be able to see questions sent from your fellow attendees in that box, and you can vote for the questions you would like to see answered by clicking the thumbs up beneath each question. At the end of the webinar, we hope that you take a minute to provide us with your feedback by completing a short survey. Finally, this webinar is being recorded, and a copy of the slides and a link to the recording will be emailed to you following the conclusion of this webinar. Now, it is my pleasure to welcome Mansour, who serves as the webinar officer for our Nonlinear Optics Technical Group. Mansour will tell you a bit more about the group and introduce you to our presenter. Mansour, the floor is all yours.
Thank you very much. I'm sharing my slides. If you have them, please just tell me. Do you have my slides, please?
Not just yet. It might take a second to load.
So I'm trying that again.
Okay.
Yeah. I hope you've got them now.
Yes.
Yeah. Hello, everyone. This is Mansour Eslami from Gbaud University, Iran. I'm very happy to host this webinar presented by Professor Peter Bienstman from the Ghent University on Unconventional Photonic Information Processing using Silicon Photonics. These series of webinars are organized and run by of nonlinear optical materials, processes, devices, and applications. Our mission is to connect the 5,000 plus members of our community through technical events, webinars, networking events, and social media. There have been many activities in the past years organized by our technical group. You see the list here, and it needs to be updated once in a while. There are several ways for you to connect with our technical group. The most obvious one is through the Optica website itself, or you can access our LinkedIn page or Facebook page, or just emailing us at tgactivities@optica.org, or just simply scanning this QR code on the bottom of this page. I am very honored to briefly introduce Professor Peter Bienstman, professor in nanophotonics, Ghent University. He received a degree in electrical engineering in 1997 and a PhD from the same university in 2001. He is now a full professor at the Department of Information Technology. His research interests include several applications of nanophotonics, in particular unconventional photonic information processing that we're going to hear more about today. We are all ears. Peter, please have the mic. Thank you.
Okay, thank you very much for the introduction, and thank you very much for the opportunity to present our work here. Let me try and share my slides. Okay, they should be going up now. I'm assuming you can see them. Okay, So yes, indeed, what I would like to do today is walk you a little bit through the different applications that we've been studying in our quest to exploit silicon photonics using rather unconventional AI-inspired paradigms. And the first thing I would like to do, just to whet your appetite, is show you a picture of a chip that we made already quite a while ago. So it looks pretty mysterious, and you might wonder what can we actually do with this particular chip. Well, it turns out that with this chip, you can do quite a lot of different things. So for starters, you can do arbitrary Boolean calculations on a bit stream. So you can calculate the XOR of the current bit with the previous bit, or the NAND of the current bit with 3 bits ago. So these types of memory-based calculations. You can do bit stream header recognition, telecom signals equalization, but also more analog types of signals like speech recognition of isolated digits. And the nice thing about that particular chip that we introduced at that point in time was that it did not consume any active power. And as we will also show later, it's quite easy to scale this thing up to very high processing speeds. And the way we do this is by taking an inspiration from the field of machine learning, namely the reservoir computing paradigm. Now, what is reservoir computing and how does that fit in the larger zoology of different machine learning paradigms that exist nowadays? So obviously, if I make a very grave oversimplification, on the one hand, we have the feed-forward neural networks, which is basically where most of the research is happening nowadays. So this is your ChatGPT, basically, which is in essence just layers of matrix multiplications followed by nonlinearities. So information flows from left to right, and this is why it's called a feed-forward neural network. Now, these things are extremely large, especially for large language models. You have billions of free parameters. And since this thing is a static system, it's also most naturally suited for processing static input like images, which of course does not say that you cannot process time series with it, but then you have to sort of like spatially unfold the time dimension into the different input channels. So this is what most people are doing. What we're doing, on the other hand, is something a bit different, is using recurrent neural networks. So you see there in the diagram that rather than the information just flowing from left to right, you have all sorts of feedback loops. And these feedback loops, they actually create memory in your system. And this turns your system from a boring static system into a rich dynamical system with lots of interesting behavior. Now, because this is a dynamical system, it's also very naturally suited to process time-varying inputs. But the disadvantage is that these things are much harder to train than the feed-forward neural networks. And this is one of the reasons why most of people nowadays use the feed-forward neural networks. But still, there are some advantages to these recurrent neural networks, as we'll see later on. Now, because originally these things were quite hard to train, and now we're talking about more than 20 years ago, people have been looking at alternatives to use these recurrent neural networks by sort of like tweaking the training mechanism. And this is where reservoir computing entered the scene. So it turned out originally to be quite successful in things like speech recognition, robot control, all sorts of time series processing things. And especially successful in situations where there was lots of noise present. So this seemed to be a very robust technique against all sorts of environmental perturbations. But of course, originally it was mainly implemented in software, and this is basically where we want to come in by taking this software-based paradigm and see whether we can implement this in photonics. But before we go there, let me briefly talk you through the main working principle of reservoir computing. So I've drawn there in the middle in this yellow box the reservoir, which is this recurrent neural network. But the main peculiarity here is that since this recurrent neural network is so difficult to train in practice, we're just going to say, well, let's not bother, let's not train it at all, and let's just randomly initialize it. So then we have a fixed recurrent neural network, and this is our reservoir. Obviously, we still need a system to be able to perform some sort of useful task. And this is where the second layer comes into play, which is the output layer over here. But this is an extremely simple layer. It's just taking linear combinations of all of the different time sequences that happen at the different nodes in the reservoir. And since this is basically linear regression, it's something that you can do very easily with a single line of Python or MATLAB code or whatever. And it does not need, in general, these complicated iterative training mechanisms like backpropagation, although sometimes we also do use them. But the main message here in reservoir computing is we have a recurrent neural network, but we're not training it. We're just randomly initializing it and only training the readout that comes after it. This may sound a bit strange because actually what we seem to be doing is we come in with a complicated time sequence over here in the input, and then we make this thing even more complicated by sending it through this nonlinear dynamical system. And then the hope is that with an extremely simple linear classifier, we're able to do something useful. So that sounds a bit mysterious. So where does this thing actually come from? So that's something interesting to keep in mind that we'll discuss in just a moment. What's also very interesting is that for the tasks that we're interested in, that I'm going to discuss later, is that we don't really need these huge networks of a bazillion number of nodes, but very small networks, because they're also recurrently reused in time, we can still do useful tasks. And that's very interesting for hardware implementation. And basically, as soon as you have a nonlinear dynamical system, you can use it as a reservoir. And for our nonlinear dynamical systems, we will be using integrated photonic reservoirs. But to come back a bit about this question I mentioned earlier, why is it interesting to make our symbols first more complicated in order to solve them with a simple linear classifier? Well, it all comes back to something which is quite familiar to the people in machine learning, which is a problem called overfitting. To illustrate what overfitting is, I've here a data set of the price of a house versus the size of a house, and the crosses here are different data points. And if you fit a certain model through this, the goal is that you sort of capture the underlying behavior. So if you fit a second order polynomial to this, you more or less capture the behavior, apart from the saturating part over here. But you see that there's still some mistakes that you make over here. So naively, you might think, okay, if I just throw more degrees of freedom at this problem, I can perhaps improve my fitting. And indeed, you can improve your fitting, but then you can run into this famous problem of overfitting, which is where, and that's what you see in this slide, you basically learn your training data by heart. The model that you fit goes exactly through all of the points, all of your data sets. But you see in this case, you cannot really generalize to points that you haven't seen before. So that's a big problem. And this is why people tend to prefer models that are as simple as possible, that have as few degrees of freedom as possible. And this is exactly where reservoir computing comes into play, because it sort of like fixes this problem of overfitting. Because what's happening is it takes your data. So for example, here you have data which is non-linearly separable by this complicated nonlinear boundary, which is also very sensitive to, for example, measurement errors, because if it turns out that this point over here is a measurement error and should actually be lying over here, you've basically wasted your degrees of freedom to learn the training data by heart. So this is not what you want to do. You want to have a boundary which is as simple as possible. But okay, sometimes your data is what it is. In this case, it's not possible to draw like a linear boundary to separate these two classes. But with techniques like reservoir computing, you can take your data from a low dimensional space and then move it to a much higher dimensional space. And there, in practice, it turns out that the different classes, the different examples of the different classes will still cluster together. And now you can separate your data with a very simple, boring linear classifier, a hyperplane in this case. So because this is a simpler classifier, it's not as prone to overfitting. So that's the whole goal of this reservoir computing business. It's basically a nonlinear filter which takes your data into a higher dimensional space where a simple linear classifier can do something useful. That's all there is to it. And this is indeed what this chip that I've shown earlier is implementing. So you come in with light over here and in this particular port, and then you take this light through some sort of multipath interferometer through this chip. The circles that you see here, they're not ring resonators. It's just like an abstract form of the network topology superimposed on the SEM image. So if you look at one certain output port, for example, you will notice that there's different ways of going from the input to the output, and like the arrows indicate a recurrence that's happening. So basically, each output contains many delayed and mixed copies of the inputs. And this is your transformation to a higher dimensional space that we're after. So it's a very simple case, it's a very simple thing to build in silicon photonics, mature technology. The only thing you're needing basically is splitters, combiners, and waveguides. So you do not need to integrate any active component in this case. The only nonlinearity that we use here is the nonlinearity that you would need to have anyhow at the output, where you have a photodetector. And this photodetector takes a complex valued amplitude and phase electrical field and transforms that into the absolute magnitude squared, namely an intensity in the electrical domain. So this nonlinear squaring operation causes all the interference to happen and all the nonlinear processes. So it's a very simple technology, almost trivial, I would say. And again, nothing that consumes active power on this chip. And there's also nothing that limits the timescales here. What is also very interesting, and if I go back to our picture over here, is if you look in between two nodes, you have this structure over here, which is actually a delay length, a delay spiral wrapped up in a very compact footprint. The goal of this delay line is basically to slow down the dynamics such that it becomes compatible with the capabilities of our measurement equipment, basically. So if you do not have this time delay over here, then we calculated that this chip can basically run at line speeds of almost up to 1 terabaud per second. I mean, there's no modulator that can even modulate this fast. So it's an extremely future-proof technology where we actually have to spend effort to slow down the speed of the system, rather than like you would typically have in other technologies where you would need to work very hard to speed up the technology. So it's a very future-proof approach. And again, the same generic chip can be used for many different tasks. Now, obviously, just because you can solve a certain task with it does not mean that it is a good idea to solve a particular task. The tasks that we're really interested in, our preferred set of applications, is where the input is already in the optical domain. So that means it makes a lot of sense to try and also do the processing in the optical domain, that you do not lose any power going back and forth between electrical and optical domain. And typically where you have the need for high throughput and low latency, where electronics suffers, for example, where it could be costly or difficult to implement that in electronics. And also already mentioned, this thing will not scale to a very large number of nodes because of the footprint issues and loss issues. So we're looking for applications that can have really interesting performance with a very limited set of nodes. So we're talking 10, 20, 30 types nodes. One logical application where we ended up with is telecommunications, basically, because the goal, what we're trying to do here, is use this reservoir approach to do dispersion compensation for different types of links. And I will briefly take you through a couple of these examples here. So again, to set the stage, obviously, if you send input through an optical fiber, at the end of the fiber, you get this spaghetti eye diagram where it becomes very difficult to distinguish the zeros from the ones. This is where the electronic DSP comes into play to clean up the signal such that the eye opens. But our goal is basically to replace this expensive, power-hungry DSP and do the processing not in the electronic digital domain, but in the analog photonic domain. So the idea is to have this reservoir chip in front of our detector and do this processing such that the eye diagram opens, basically. So that's the whole goal. Now, our initial experiments were very much proof of concept that didn't really scale to a real application, because what we did was a so-called electrical readouts. So you have the chip that I showed earlier, and then what you would need to do is at each of these output ports have like a high-speed photodiode, a high-speed ADC converter, and then doing this weighted sum in the digital domain. But obviously that does not really scale because you cannot have a large number of high-speed ADCs on a chip. And also in practice, to do these experiments, we did not even do that. We cheated because we took a fiber that we used to sequentially measure all of these channels one by one and then realign them and process them in offline on a computer. But very recently, we've been able to move to what we call the optical readout scheme, is where we also do this readout, this linker combination, in the analog optical domain with complex valued weights. So basically modulators that you use to weigh these different symbols, then you combine them in the optical domain, and you only need a single photodiode and a single ADC. This comes at the expense of a little bit more complicated training. So here we do need some iterative training approaches. But of course, the advantage is tremendous because this thing will run then in real time and does not require a very large electronic footprint with lots of ADCs. So to give you a flavor of what this chip looks like, it's not the most photogenic picture, but here you have this reservoir over here. And then here you have the weighting elements with electronic control to set the different amplitude and phases. And then we combine them, and then we have the output at the very end. Okay, so we take this chip and we try to perform real-time dispersion compensation also for highly nonlinear links with this. So this is why we have a setup like this, where before the fiber, we have an amplifier to really boost the input power such that we really hit all the nonlinearities in the fiber. And then we have another amplifier after the chip to make sure that the combination here of this whole chain has a fixed I'm sorry, that's the goal of the second amplifier rather. So we're trying to make sure that we're really doing an honest comparison in terms of signal to power ratio coming into the reservoir chip. And then also at the very end, we have an extra amplifier to compensate for still a lot of residual losses that we had in this iteration of the chip. Okay, so this is the link that we have, and then we have some control electronics to do the training to set the weights. But then once the weights are set, this thing runs at high speeds in real time. This particular experiment was done at 28 gigabit per second of keying. So these are the experimental results where we measured the bit error rates for different fiber lengths. And there's some interesting lines to look at. So what you have over here is a bit error rate of about 10 to the minus 4, which is one of the forward error correction limits. So if you're below this limit, that means that you're in good shape, and then some post-processing can take over and get rid of the residual errors. This was the measurement error of the bit error rate in our experiments. And we see here in this blue curve that we're really very far below this FEC limit with bit error rates basically below 10 to the minus 5. Just to put this number in perspective, experimental results on the same chip but with an electronic feed-forward equalizer has a bit error rate which is orders of magnitude higher. This is, of course, a linear equalizer, so it's logical that it does not perform as well as our nonlinear reservoir equalizer. Of course, there's nothing that says that you cannot also do this nonlinear equalization in the electronic domain in this particular case. But of course, here what we're showing is that we can also do this at high speeds, real time, in the analog optical domain. This was for a given input power and varying the fiber length. You can also have a fixed fiber length and then crank up the input power to really hit this nonlinear regime. And then indeed you see that it becomes more complicated. The bit error rate goes up for high input powers. This is a very nonlinear regime, but you still stay below this FEC limit. So that's good news. To visualize this in a different way, this is the eye diagram without any post-processing. Electronic tap delay line turns it into this, a little bit more open. It's still very hazy here in the center. If we do the same thing now with the reservoir experiment, the eye really opens up. So we're very happy with this result because this really shows that without any sort of like offline processing, you do these chips to equalize very highly nonlinear telecommunication links. This was for on-off keying. We've also been looking at coherent links because that's, of course, where the things become more challenging and also more interesting. So also here we have a set of experiments, but just as a caveat, this is the experiment where we still use the so-called electrical or parallel readout scheme, where we took a fiber and sequentially measured all of the different channels and then realigned them afterwards on a computer. So our next goal is, of course, is to do also a similar experiment like this with the all-optical readout that I presented in the previous section. So a very similar type of link. This time we have a QAM modulator instead of on-off keying. And also for comparison, we have here an attenuator, which roughly has the same losses as a chip for our benchmark, such that we can really compare apples to apples here. Okay, very standard optical setup where we have collaboration with people in Aston University to help us with the high-speed equipment. And yeah, these are some images of the constellation diagram that you have at the input to the chip. And then what really happens at the output, you see this amorphous blob here is now nicely separated into the 16 QAM here constellation diagram. Okay, so obviously this also works with lower order constellations, QAM 4, and this is again the QAM 16. Very important here is that we do not consider this reservoir approach in isolation because we don't really do all of the different DSP steps already in the optical domain, but we sort of like do a co-optimization of the analog optical part and the residual digital part. So just to illustrate what we're doing in the optical domain and what we're doing in the electronic domain. So here we have a typical DSP chain here. Very important parts are dispersion compensation and then the active equalization. So these are the time-consuming parts that actually do the equalization, and the rest is just related to like clock recovery, carrier phase estimation, and things like that. So we take these two important blocks out of the DSP chain and we move them up front such that we do them in the optical domain. So very important for getting good performance is that we don't optimize this optical part in isolation, but we really take into account a co-optimization of the whole chain, also including the residual DSP. And this is where we get the most benefit. Important part is that the most time-consuming calculations, they're now in the analog optical domain. So experimental results here, bit error rate as a function of input power. This is the benchmark case where we do not have a reservoir, but just a regular DSP chain as you would normally do. Okay, so again, you have a more linear situation at the beginning for low powers and lots more nonlinear distortion for higher powers. Now, how does our reservoir compare in this case? You see you have roughly the same performance, sometimes a little bit better even, but the very important part is that we now offloaded this to the analog photonic domain. That also means that you do not require as stringent of a sampling requirement, so you do not need 2 samples per bit here. This thing just runs completely in the analog domain, this active equalization part. Okay, so that's good news. So just to wrap up where we are here for the time being. So I've illustrated what reservoir computing is, showed how it can work in coherent links and in intensity modulated links. What I would now briefly like to illustrate is how we can also exploit the wavelength dimension, because that's of course something that photonics really has as an inherent advantage. So it's important to exploit that. And the goal that we have is actually trying to build a system where, again, we have a reservoir followed by a set of weights. But the goal is that we process a certain task like dispersion compensation on different WDM channels in parallel with having exactly the same set of weights operating on all the wavelengths in parallel. Because that way we can really increase the throughput per footprint of our system, because otherwise we would need a separate reservoir for each wavelength, and that would not be economical. So the goal is, can we design a chip that does precisely that, having the same set of weights for all different channels in parallel. So one way of doing this is making use of the physics of the problem. It's basically saying, okay, if my light travels from one node to the next node, it will see a certain phase delay. But if I then engineer my interconnection lengths in such a way that if I go from lambda 1 to lambda 2, the difference in phase is exactly 2 pi, that means the system will behave identically for lambda 1 and lambda 2. So that's a naive thing we could try. We just train the system for lambda 1 and we design it in such a way that we have different wavelengths for which this would work at a 2 pi phase shift. That's, of course, the theory. In practice, there's all sorts of things like dispersion going on. So the question is, will this actually also work if you take waveguide dispersions into account? And the answer is yes, indeed. It still works very nicely. You get good performance at the central wavelength channel where you train, but also automatically at neighboring channels, dozens or even hundreds of different neighboring channels. So that's good news. But of course, you're limited by the physics, the 2 pi. If you want a little bit more flexibility and you want different wavelengths that have an arbitrary separation from each other, then you can have this approach, what we call multiple wavelength training. So we not only train for a certain wavelength, but in our training set, we also take examples from a different adjacent wavelength into account, such that we now really ask the system, the training algorithm, to get a system that works as well as possible for two different wavelengths. Of course, this is slightly more difficult from a machine learning perspective, so we do expect the performance to slightly go down a little bit, but still seems to work rather nicely. The disadvantage here is that this does not work for dozens or hundreds of different channels. You're limited by 2, perhaps 3 or 4, but not more different channels, because the machine learning problem is basically so much harder. But what you can do is play a very nice trick. This multiple wavelength training, you can also use this to increase the robustness of your system. Because you see here that the region of good performance with low error rate is actually quite narrow. But what you can do is actually in your training, take into account different wavelengths that are adjacent, that are very close to each other, as opposed to the previous case where the different wavelength was over here. But now the goal is rather to broaden this operational range, such that you're more robust against, for example, chirp in your laser or whatever. So again, taking this into account during the training actually seems to help. And this is what we show in this simulation here. If you only train for a single wavelength over here, you have this very narrow green operational region. If you, on the other hand, train for this wavelength and for that wavelength, it's basically a window that increases by a factor of 2 or 3. So just by having exactly the same hardware, but tweaking the training algorithm, you make the system more robust. So that's good to have. And the nice thing is you can also combine this with the 2π trick, such that you have a very robust wide performance range combined with many multiple wavelength channels. And indeed, that works. So these were all simulations. We've also done this experimentally with, again, a very similar experimental setup, of course. And what you see is indeed what you would expect. If you only train for this wavelength channel over here, you get good performance at that central wavelength channel, but bad performance at other wavelength channels. On the other hand, if you train for all of them in parallel, you get good performance for the whole operating range. Small caveat here, what we're not doing yet is sending these different wavelengths in at the same time. So we don't capture things like cross-phase modulation. So this is like a first step towards that, where we show that with the same set of weights, we can equalize different channels separately. And again, this also works if you go to the highly nonlinear case, where you have lots more nonlinearity. If you go from 10 dB all the way up to 18 dB, you get very far below this FEC limit. Okay, so this was also showing how you could exploit WDM. What I would now like to do in the last 10 minutes of my talk is talk a little bit about something which is a lot more exotic, no longer related to like a concrete task like telecommunications, which is trying to build reservoirs that can adapt themselves autonomously and see what type of emergent behavior arises from that. So ideally, the holy grail would be to sort of replace the current way we train these things by something that can work completely autonomously. Because what we're doing nowadays is we still, for the training, do things like linear algebra or backpropagation, which requires that we're able to measure the signals and that we have some sort of global omniscient entity which observes everything and then sets the weights, which is not biologically plausible and is also not something that scales very well. Would be much more interesting to have complete self-learning, the way we have in our brain, but that's of course a little bit too ambitious for the time being. So here we have some sort of intermediate step. We still stay within the reservoir computing paradigm, where we train linear regression after the reservoir. But the question is, can we, rather than have a fixed reservoir, have a plastic reservoir that autonomously self-adapts itself to a certain task without any feedback loops, without any global reward signal? So the question is, can we do that? Now, in order to be able to do that, we need some sort of memory in the system that can store everything that the system has learned so far. So for that, we use phase change materials, GST, which we optically address, such that optically we change them from an amorphous state to a crystalline state and back, which means that the transmission changes. And this is a non-volatile change. So this programming changes basically right until we reprogram it again. So we have some sort of all-optical memory. So the architecture we're looking at here is also a bit different. You have all of these coupled ring resonators in different rows and columns. So to zoom in a little bit, this is what this looks like. These tiny patches over here, this is the GST, the phase change material. So it's quite lossy, which is why we do not cover the entire ring resonator with this, but only like this small patch. Of course, here I need to acknowledge our collaborations in Münster and Oxford for the GST deposition and the E-beam fabrication. So the thing is, we've also been looking at models to try and understand this system. We have some sort of equations, but they're very complicated, have lots of different timescales. So we can only model extremely small networks of these things. As soon as you move to a lot of different input channels with a lot of different wavelengths, this becomes completely impractical to model. So this is why we moved to experiments instead. And the question is, how can we use this chip and do something useful with it? So are there ways to maximize the data that we get of a single chip? And can we show that plasticity is really helpful in this case and not just a gimmick? Okay, just to walk you through what we have here in order to try and maximize the information content in a given chip. We have, again, our network of coupled ring resonators, but we have several different ways of exciting the system. First of all, we can have the input in different spatial channels here, but we can also have the input in different wavelengths. So obviously, because of fabrication imperfections, not all of these resonances will be aligned. And possibly, for example, if you excite with this so-called green laser over here, of course, it's all infrared, but just for visualization purposes, then these green rings will start to resonate. If you excite it over here with this purple light, then the purple rings will start to resonate. So this is a way of having a single physical chip, but overlaid on top of that, many different interacting virtual reservoirs by playing with the wavelengths and with different input ports. And each of these chips has many different nonlinear effects with different timescales. So you have thermal and free carrier nonlinearity, but you also have this very long timescale with the plasticity of the PCM in certain rings. So this is this complicated sort of like many superimposed reservoirs on top of each other, which all interact. First question is, does actually something change if we send in different input signals through this chip? And indeed, if you look at the spectrum, if you zoom in here, you see some changes in the transmission characteristics. So you see indeed something happening. It looks very subtle, but the change is definitely there. So at least this tells us that the network is plastic and it can adapt to the types of input that you send in. Of course, you need to have a certain power level in order to hit this plastic regime, which is also something that we can exploit to try and understand what's happening. As soon as we are above this plastic threshold, we can let the system reprogram itself, and then we can lower the power below that threshold and then see what has actually happened. And this is what we're trying to do to understand what's going on. We're going to look at an extremely contrived task with very separate learning and adaptation steps. It's a task which is not useful at all, but it's a task that hopefully gives us some insights into what's happening and whether or not this can be useful to have self-adaptation. So the task is the following. We want to distinguish 5 different bit patterns that all have the same average power. And we want to do that by measuring only the average power. Of course, since they all have the same average power, this is something that really requires nonlinearity and memory in order to solve this task, because otherwise, obviously, there's no way to distinguish them by just looking at the average power. So we also have a very special wave form of these different patterns, such that during learning, we can increase the power of the final bit to trigger the plasticity. So this is what this looks like. These are the different patterns that we want to distinguish. They all have the same average power, and we want to measure the average power. And they also all have, in the last point here, a bit which is 1. And during the plastic step, where we do the actual training, we boost the power of that last bit, such that basically the previous bits set up some complicated interference pattern non-linearly in this very complicated system that we have. And then once this has happened, we basically tell the system, okay, and now start to do some plastic adaptation. You raise the power of the final bits, and then we do things again and again. So we keep on showing it examples of all of these different bit patterns. And the hope is that by doing this, the reservoir will sort of like self-adapt in a mysterious way because it has learned to pick up on some correlations or the type of things that are happening in these systems. And that's what we're going to do in the experiment. And indeed, you see that something interesting is happening because if we then test the system after this plastic adaptation step by having low power input that we need to classify, you see initially you have a very high test error rate, which is basically 1 in 5, just random guessing. But then as the training procedure proceeds, as the number of steps that you allow the system to sort of like reconfigure itself increases, that this test error roughly on average goes down. Sometimes it goes up again and then goes down again, which is not too dissimilar to what you also find during training of neural networks. So perhaps there's some exploration going on, looking for a different local minimum and then trying to optimize things. So strangely enough, on average, the error goes down. Of course, yeah, this is an extremely boring task, doesn't really tell us anything that we can use it for something more interesting. So this is why we're looking at the so-called MNIST handwritten digit recognition task. So also there we cannot really play this trick with having a final bit which is high or whatever. So what we're going to do is have the system always operate in its plastic phase, so no longer separate learning and inference phases going on. So lifelong learning if you want. And also because I mentioned earlier that sometimes the error goes up, and that's not what we want. So we also want to exploit the fact that within the same physical chip, we can have many virtual chips and then cascade these virtual chips such that the error of the first reservoir gets compensated by the next reservoir in the chain. So we have a combination of different techniques here to solve this task. So here we have our MNIST, different images that we want to classify. Obviously, we work not with images, but with time series. So we're going to turn this into a time series by just scanning line by line over this image. And then this time series, we will encode in different wavelengths and also send them in different input ports. We let them propagate through our reservoir. And at the output, again, we measure different output ports and different wavelengths. We can then reconstitute the image from that by doing the inverse operation here. And then you see that what we have is basically a system that takes a certain image and then creates many different nonlinear transformations of that image. So this is, again, our many different reservoirs going on. And then I already mentioned what we're doing. We're not taking a single reservoir, but we're actually having all of these reservoirs trained one after the other and having the output of the first reservoir also combined with the output of the second reservoir. And in this sort of like chaining approach, we can really improve the performance. So you see that we get a performance for this MNIST task of about 98% here testing accuracy if we combine roughly 7 or 8 different of these virtual reservoirs. So the question I always get here is what is really going on? Can we really understand that this thing actually learns? And then, to be honest, I have to say that is not something easy to understand because it's not easy to model this thing theoretically. We just have the experiment to look at. So it's not all that clear to us yet why this thing performs the way it performs. So we're trying to tackle this by working on 2 different tracks. One track is building some sort of approximate model that will hopefully help us to analyze this thing better. The other thing is to slightly modify the experiment where we do have some sort of external reward signal that we then feed back to the rings. And in that way, it becomes much more easier to also reason about the system where we can then really say, okay, if my error signal goes down, then also my rings no longer adapt. And then it becomes much more interpretable, this system. So these are the 2 approaches that we're following in terms of continuing with this work. So this 98% compares quite nicely what people have been doing in the state of the art. Okay, let me wrap it up here. So I've talked about 2 different applications of reservoir computing, one a bit more closer to the application side, which is this nonlinear dispersion compensation for different types of modulation formats. But on the other hand, we also have fun with some blue sky types of things like these self-adapting reservoirs. Okay, so I acknowledge this funding from the European Commission, and I'm happy to take any questions now.
Thank you very much, Peter, for this really unconventional topic. We enjoyed it. Thank you. And we've got a bunch of questions, and some of them are more basic than the others. I start with the most basic one, which is what exactly happens in the nodes that you call it information processing.
So the information processing is not really happening inside the nodes. There is some sort of information processing happening in the system as a whole. So what's happening in the system as a whole, and I'm assuming the question is about the vanilla reservoir computing, not the self-adapting thing. So what's happening in the system as a whole is that it takes your data that's coming in and it transports it, it translates it into a much higher dimensional space where it then can be separated by a linear classifier. So if you don't want to think about this in terms of machine learning, you can just say it's a nonlinear filter that processes your data. And that's a perfectly valid alternative way of looking at these things.
Okay, then we should look at it as a whole, not just different parts.
Yeah.
In whole, it helps you to have a higher dimensional space to classify your data, for example. Thank you very much. The next question is that is there any nonlinear interactions, light matter interactions happening in the whole device?
So in the first part of my talk, when I was talking about the telecom thing, the reservoir itself is purely linear. So we're not talking about high input powers that trigger any nonlinearities there. So this was a more boring case if you want. But in the second part where I talked about the self-adapting reservoirs, then it's nonlinearities all over the place. We have a much higher power. We also hit the classical silicon-only nonlinearities, thermal, free carrier, Kerr effect. And we also have on top of that the phase change material, but with the plasticity going on. So that's an extremely nonlinear case. So depending on your application and what you're interested in, you can have many different types of reservoirs. Yeah.
Thank you very much. And is there any cooling device? Is there any heating problems that you need cooling down the system?
Yeah. So for these telecommunication tasks, we do have some thermal stabilization. So we do have a Peltier cooler under the chip. It's not an extremely accurate one, so we have some flexibility there. And one trick we can also play, we've looked at this a little bit, is rather than training the system to be robust against shifts in wavelengths, you could also train the system to be robust against shifts in temperature, for example. So that's also something that you could try and do to get rid of this thermal stabilization if you want to. But for the experiments at the time being, we use a Peltier cooler.
Thank you so much. One question that I got just now, in the experiment with an array of rings, what if you don't use the phase-changing material? On slide 63, you have only some rings with the phase-changing materials. Why not all of them?
Yeah, this was basically, we could have done this. The philosophy behind this is to say, okay, the ones with the phase change materials, because they change, they adapt, they're more like the weights in a classical neural network. And the ones without the phase change material that do not adapt, they're more like the nodes in a classical neural network. So yeah, but again, it's a bit of an arbitrary choice. We could have had more rings or fewer rings with the phase change material on top. So it's nothing fundamental.
Yeah. And another question from the audience. You mentioned how you can engineer your chip to operate at 2 wavelengths. You also showed that one can make these wavelengths windows wider. The question is, does this limit the data transfer bandwidths? Because the higher the baud rate, the wider the spectrum of the signal.
Yeah, sure. So obviously, so if I go back, I'm not sure if it's worthwhile going back to that slide. But in any case, the requirements, if you go to higher and higher baud rates, the requirements, of course, of this thing become wider. But just to make sure that people understand really what's going on in a diagram like this, for example, this does not mean that if you have a system over here, where the central wavelength over here, that your spectral content of the system, of the signal should be smaller than this thing over here. Because what's happening here is basically the error that you get for a central wavelength with a certain spectral extent centered at this particular case. So the spectral extent is already taken into account in the performance that you get here and is not directly related to this robustness gap. So these are two different spectral features, basically, which are important not to confuse.
Thank you so much. And I guess this is the last question. Is the plastic self-adapting reservoir capable of completely removing the output training, or is it only used to assist the training?
Yeah. So this is important to stress again. So this is still the reservoir computing approach, right? So we do still have external weights that we train with linear regression. So our pipe dream very far into the future would be a system that is completely autonomous, perhaps with feeding back an output error signal. We could get there, but for the time being, this is like an intermediate step towards that. Yeah, very difficult to achieve goal, of course.
Thank you so much. And Stevie just thanks you for the great presentation and asks how the initial state of your reservoir impact the efficiency of the processing.
Yeah, that's actually a very good question because this is something I didn't mention. I'm not sure if I have a slide to illustrate this. But basically what happens if you design a certain chip with a certain length, what you fabricate, and if you fabricate it multiple times, is each time you get a completely different chip in terms of the phases that you get if you travel from one node to another node. So each chip that you make is random. So this is where the randomness comes into play. And this is also something that we need to be aware of, that if we do our signal processing, will it work for different random initializations of this particular chip? The answer is that it does. It's also something we can verify in simulations. What we typically do is we do not look at the performance for a single random reservoir, but we do it for many different reservoirs with random phases, and then do some sort of average and spread over the different chips that you have. And then you see in regions where the performance is actually quite good, that this spread is actually quite narrow. So what's happening is that the training compensates for the fact that you have different physical chips with different random phases. So that's good news, of course. It means that you're not sensitive to fabrication errors. But the flip side is that each chip needs its own bespoke set of weights because you have this random phase variation during fabrication. Yeah, but that's a very good point.
Great answer. I think there is no more questions. Thank you very much, Peter, for accepting our invitation for today's webinar. And thank you very much for the attendees for their questions and their attention. I think that's all for me here. Thank you very much.
Thank you very much. The pleasure was all mine. Thank you. Bye.
All right, that will conclude our question and answer session for today. Please remember that when you disconnect, you'll be prompted to complete a quick survey. We will also be sending you a link to today's recording by email within 48 hours. I'd like to thank Peter for taking the time to present for us today and thank our Nonlinear Optics technical group for organizing this webinar. On behalf of Optica, thank you for joining us, and this concludes today's webinar. You may now disconnect. Thank you.